Welcome to Chapter 6, Control Flow. Sequential Programming and Structured Programming. Advances of control flow. Before we go into the sequential programming or unstructured programming, let's look at the advances for the control flow in a program. So, sequential programming is the most simplest one. It's just like assembly language. You finish one statement by a statement, and maybe there is certain jump or go back to certain code. And then we have structural programming. And the sequential programming also called as unstructured. And structured programming has the sequential one, has the decision box, has the repetition, and may have a function code. And these are the single thread, single processor programming. And then later we have the object-oriented programming, and it comes with the multi-threading to support it. And we call this the early days concurrent programming. And then we have the event-driven programming. And we have event loop programming. Event loop programming is using a sequential programming to mimic the multi-threading environment. And real event-driven programming can be multi-threading as well. And above the concurrent programming, we still have the parallel programming. So these are the advances for the control flow. And the object-oriented programming is suitable to support these different concurrent programming. And the advance of the object-oriented programming is mainly because of the Windows system. The programming no longer is on the text mode. And at that time, we start to look at the object-oriented programming. Control flow. Basic paradigm for control flow. We have go-to, branch, jump, and sequencing. These are unstructured programming. That's why we are going to talk about as the first topic for control flow. And in this chapter, we will cover selection, iteration, procedural, recursion. And concurrent programming is at chapter 13. Exception handling is actually in maybe chapter 8 or 9, probably 9. That's considered a special procedure. And then non-determinacy programming. Unstructured control flow. We have sequencing, code, go-to, and code segment and section. This is mainly used for the early language, assembly language, COBOL, and Fortran. Unstructured control flow. Unstructured control flow, the use of go-to statement and the statement label to implement the control flow. Now, this nowadays we consider to be bad and also proven that difficult to trace the program or make it consistent. Most can be replaced by structured and some exceptions, break from the nested loop, return from multiple routine calls, and Java no longer has the go-to statement. In fact, there is a label, but actually it's no longer being used. Language feature to support unstructured control flow, sequencing, branch, condition, and go-to statement. These are the topics that we are going to discuss. Unstructured programming is still in use. In every language, still have the feature for unstructured control flow. But it had been replaced by structured programming to make the programming more consistent and more expressive and also more debuggable. Sequencing is easy. The execution of statement and the evaluation of expression is usually in the order in which they appear in the program text. Sequencing specifies linear order on statements. One statement follows another, very imperative, monument machine type. A compound statement is delimited list of statements. A compound statement is called a cobra. So usually when we see in the C language, we see this, or Pascal language, we have begin and end. And some languages like Python is by indentation. Now we call a cobra. Here, let's look at the C double plus goto statement and the assembly. On the right hand side, we have the C goto statement. So basically, it's essentially C double plus. We declare I equals x equals 3, and then we go to this, and then there is a statement of this actually will not be executed, and then we return x. And then in assembly code, we move the 3 to the register, and then jump to lemma alta here, and then we return the value from the register, and this one can no longer be can never be executed. That's the goto statement. Assembly branch and jumps. On the right hand side, we have many instructions for the jump. It has always jump, unconditional jump. Sometimes we call it unconditional jump in the assembly language. So jump is actually unconditional. And then these, the rest of them are conditional. Jump from grade 2, jump grade equal, above or equal, jump below or equal, jump unsigned, overflow, and then jump equal, jump sign greater, jump sign greater than, jump sign less than. So this one is the unsigned comparison. Basics is related to the representation of the register. So many others. Here's how to compare and jump if equal. So we move 3 to register, and then compare 3 with it, and it will set flag. So basically, this compare statement will set some equal flag or something, and if it is equal, we jump to here. And then this one is jump less than. Same thing is actually will compare a flag. So this one, when do comparison, it will actually set some flag. And based on the flag condition, the jump statement will jump to the location that you will go to under a certain condition. So, and usually those flags are there, will be assigned in the processor status register. Code segment. Code segment is used in COBOL language. It implemented by jump and branch. And COBOL is like a book, so it has division, section, paragraph, sentence, and statements. It's of different hierarchical structure. but these are not really a good design because there's too many kind of name. So COBOL is like a book. So you have main, you have 300 housekeeping, you have 500 mainline processing, 530, 555, 550, 700. That's all different code section. So basically, section 000, it has some data and some code. And then there is a perform 3300 and through this and exit. So here are some code. When you get started, you will go here and then jump somewhere to perform and then come back. Expression evaluation, number 1, continue and exit condition. So now we go into the structural programming. In structural programming, we basically has if then else, the selection or decision. That's selection. Iteration, we have for loop. That's iteration. Procedural abstraction, we have some code block, and then you pass the parameter in and get started to run and then go back. Recursion, is calling on the functions. These are the structured programming, and it's proven that all of the unstructured programming can be replaced by structured programming code. Expression is evaluation. We have infix, prefix, operator. Precedence associativity. See figure 6.1. We will later look at it. So here we have infix, postfix, and prefix representation. And each one had different evaluation rule. And for C language, we have 15 levels. And Pascal has 3, Fortran has 8, Ada has 6. So basically, a expression can be written down in infix, prefix, and postfix format, but depending on the language. And then there's another issue of precedence associativity. Let's look at the infix. Infix is actually A plus B plus C plus D. This is a normal representation for operator in the middle for binary operators. Postfix, we had an operator at the end. So this one actually means A times B plus C in the infix condition. And the prefix had the operator in front. This one actually is for prefix. Prefix had the operator in front. And then expression has another issue of precedence associativity. Let's look at it. For C language, we have 15 different levels. So anything upper would be executed first. And then Pascal has only 5 levels. Ada have about 9 of them. So you have to check each language for how many levels are there. Expression evaluation. Ordering of operand evaluation. generally none. Application of arithmetic identity. Distinguish between commutativity and associativity. These two are actually different. So this one, a plus b plus c, work if a is not equal to maximum integer and b is not equal to maximum integer, and c less than 0, and this one does not. So we need to be careful about the associativity. The since that we actually process this part first, and then with this. And this one is like we push into some stack, and then we actually operate this first. And then because of the order of the execution, the result may be different. And why I didn't worry about maximum integer is because when you have a equals a maximum integer, b equals a maximum integer, it will be overflow right away. And then this one less than 0 is a negative number. Expression evaluation, short circuit. When we have an AND and the front part, I'm sorry. When we have an AND the operator, and then the front part is false, the whole logic will be expression will be evaluated to be false. That we call short circuit. And if there is an OR, and then the front part is actually true, the whole thing will be evaluated to be true and bypass the second part. That's called short circuiting. If A greater equals 0, B, there is no point evaluating the B less than C, because A less than B and B less than C, B less than C is automatically false. Other similar situation, if we have the B not equals 0 to be true, then we will evaluate A divided by B equals C. If B is already a 0, we won't evaluate the second part. Then we will not have the arithmetic overflow problem. And this one is a pointer value P. If P is 0, that is false. That is also null. Then we won't evaluate the pointer. Then there is no null pointer problem. So, but if this one is non-zero, the second part will be evaluated. Similarly for this one, if f equals 1 or non-zero value, we will evaluate the messy part. Otherwise, it will be bypassed. Expression evaluation. Variable as value versus variable as reference. So when we evaluate the expression, there's evaluation by value and evaluation by reference difference. Value-oriented programming language are C, Pascal, Ada, and reference-based is more like a functional language, Lisp scheme, ML, Clue, Smalltalk. August 68 is kind of halfway in between. Java deliberately in between. Built-in types are value, reference type are actually object. So reference type are indirect. It will compare the object value. And in fact, there is two different evaluation. One is using double equal sign. One is using equals function. So this is not exactly the same. It's deliberated in between. So if value-oriented B equals C is the same, but if on the right-hand side we have a reference-based oriented B and C pointing to the same object, that's the model we use. This one's value-oriented. It's like a primitive data. We put some data in the memory location. Two of different memory location, but with same value. Expression evaluation. Some languages like Java, it also provide the reference model using boxing and unboxing. So primitive data type can be auto boxed or auto unboxed. And that actually make the Java language more convenient in converting from primitive data type to object types. Expression evaluation, expression oriented and statement oriented programming language. And the functional language are more expression oriented, and most of the imperative language are statement oriented. C is kind of halfway in between, because C and Python, those language try to have some functional programming features. Expression evaluation number 2. Orthogonality. What is orthogonality? Feature that can be used in any combination. So whatever it is, for example, if it is a Boolean value, it should be able to fit into any Boolean value's location. But if it is not, it shouldn't be there. For example, like C language, we can evaluate A double equal B. That would check the value. And this one is an assignment. But the side effect of the assignment is that it will return the value of the B value, and that is, if that is non-zero, then this will be true. So that actually is related to the orthogonality. You should allow only the type that return the right type, but some languages allow this side effect to be existing. So here, for example, we have a logic statement, and inside here we have another if statement, and that if statement, if return the Boolean type, then you can put in here, that we call it orthogonality. And same thing here, if it returns some logic value, we put it over here, that we call it orthogonality. Expression evaluation special cases. So we have the combination assignment operator A equals A plus 1, or B dot C element 3 dot D, and then we can have the B dot C element 3 dot D times E. So these two operations can be written as the right-hand side, as long as the variable is actually what we mean. For example, if this B dot C number 3 dot D return actually a left-hand side value, it should be able to fit at any left-hand side location. So the right-hand side would be okay. For example, if a function is actually has a input I and it's an index function, and that function calculate the index based on I value, and it will return an index. And since it returned an integer, and we will allow it to be put into any location that the integer is allowed. And now we call it another example of orthogonality. And same thing here, if it is an integer, we put it here, and A actually is a element. It can increase it by itself since it is that element is a integer, then it will be allowed to be increased. And same thing for post increment. And side effect of a function as parameter, we can pass a function as a parameter, but some of index can be calculated by that function. But this is not safe because we don't know whether this function index will exactly the same as this after the first calculation. For example, if the index function has some state variable over there, a static variable over there, and this function return value will not be the same, even though we are expecting they to be the same. And these two are equivalent, and these are equivalent. Expression evaluation, initialization. And when we evaluate the expression, we can use that to do initialization. Pascal language has no initialization facility, only by assignment. Aggregates. Compile time constant value of user-defined composite data type CC double plus A function anonymous index, anonymous object. So this actually is talking about, for example, in Java, we have this 2, 3, 4 for an array, or if we have new integer for the anonymous array. That's called aggregates. Expression evaluation. Statement or expression executed in for its side effect. Sometimes we like the side effect. Assignment operators is handy. It avoids redundant work or need for optimization. Perform side effect exactly once. C language, we have minus minus plus plus for postfix format form, and it can be pre-increment or post-increment. Expression evaluation side effect. We often discuss in the context of functions. A side effect is some permanent state change caused by execution of a function. Some noticeable effect of call other than return value. In a more general sense, assignment statement provide the ultimate example of side effect. They change the value of a variable. Side effects are fundamental to the whole Neumann model of computing. In pure large functional or data flow language, there are no such thing as side effect. These languages are called single assignment language. Single assignment means no side effect. Expression evaluation. Several languages outlaw the side effect for function. It's easier to push things about program, closer to mathematical intuition, easier to optimize, and often easier to understand. Both side effects can be nice. Consider the random number generator, RAN. It will return you a value, but the state will be changed. So each time the random number return different value. That's one of the side effects. And on the right hand side, we have a equals 0, and then we have x setter. When we set this x, we actually have n, and then n assigned to the global variable x. So x got changed. That is a side effect for this function. Expression evaluation. Side effects are Side effects are a particular problem if they affect states used in other part of the expression in which function or a call appears. So sometimes side effect is not good. It's nice to not to specify any order because it makes it easier to optimize. Fortunately, it's okay to have side effects, so easily depend on the language as well. They aren't allowed to change other part of the expression containing the function call. Unfortunately, compilers can check this correct completely, and most of them actually don't check it. So overall side effect is talking about, when we talk about side effect, you need to consider the context of the function, where they are, will they change the state variable or not. So some of noticeable effect of the call is you may permanently change some number. Control structure selection. Structural programming. Structured programming is a programming paradigm aimed at improving the clarity, quality, and development time of a computer program. And structured programming is introduced around maybe 1960 something. So by making extensive use of subroutine, block structure, for and while loops, in contrast to using the simple test and jump conditions, which lead to spaghetti code, causing difficult for both follow and maintain for the non-structured. So here we have a sequential statement, conditional statement or decisions, and also repetition or while loop. Structured control flow. We have statement sequencing, we have selection, if then else, and the switch statement. Iteration, we have for or while loop, or do while loop. Subroutine, we have functional call or methods, and it includes a recursion, all of which promote structural programming. And there are also some break level. A break level is to finish your program, either pass for do nothing, continue to actually break from the current iteration, and break function to break the whole loop, and return function to return from a function, and exit to actually quit a program. These are 5 different break levels. Cobra. Cobra, we have statements, compound statements, progress structure loops, or procedure or functions. Selection. This selection, we have the conditional statement, we have if then else, we have if else if and else, we have switch statement. So in this, we have this type of condition call, and then the effect. So C is cause, E is effect. So this is equivalent to if then else, or if then else statements like this. C case switch case. We have the expression and we can evaluate the value and then determine which case we take and to jump there to execute. Loop B has the if, else, and end structure. Selection. Function computed goto. So sometimes there's a jump call. We know jump call is not actually good. And for selection and logically controlled loops. No point in computing Boolean value into a register. So here is some discussion for some selection. So for the computed goto, actually is used to provide the jump call or the flag, sometimes we call about it. That provides some sort of selection. And then this actually is not a good idea because it depends on the instruction and also it's not very expressive. So later, jump is useful in processing or shortcutting. And actually later we use the if then else statement in Pascal language. But here we have the code generation without short circuiting. So here if we have the if statement A greater than B, so we load A to register 1, B to register 2, and then we compare. We got the partial result for R1, and we have the compare result for C and D, and the result in R2. And R1 and R2 we assign to R1, and then we have the E to E and F, and we compare the two, and then we set it to R2, and then R1 and R2 we do OR, and after that we use the result in R1, that's the whole expression, to determine to go L2. So L2 is the else part, while L1 is the then part. So if this is equals 0, that means this is false. We go to else part. So you go to L2. Otherwise, we will go to this then close and then go to level 3. That's the join point for the else statement. So basically, the assembly structure has this. We continue to go, and then there is a checkpoint. You'll go to label 2, and then we go into here and finish, go to label 3, and then label 2, finish, joining at the label 3. So that provide the if then part and else part. Using the assembly code. But this one has no short circuiting. And the version with short circuiting is we insert the short circuit so that we'll directly jump to the short circuit location. So the first part, if it is not true, if this one is not true, we directly go to L4. And if the whole front part is not true, we directly jump to L1. To do the length part, it is actually 1. Jump table. Jump table is used for the case switch statement. So here we have the address for the label L1, L2, L3 to L whatever number it is over here. So here actually we can call this as a jump table because it's an assembly. So here we have a table and it stores many edges over here. So here actually we start with calculating the expression and the expression being put into R1. So R1 is actually the expression. And if it's less than 1, that means that no case is assumed. So we go to L5. We directly go to L5. That's the default statement. If it is greater than 10, we also go to default. And if they are not, that means that these they are within one of the case. Then we do this. We use the value in R1. So R1 minus 1. R1 decreased. R1 is over here. It has a value for the expression. And then we actually use that value. That if it is 1, if R1 is actually the expression, if it is case 1, then we go to we will let the R1 become if actually R1 is currently 1, we decrease by 1, that make R1 to be 0, and then we use that 0 from table here to get the first entry. So this one actually is the HS calculation for the table, and then in case that R1 after decrement becomes 0, we go to have this the first label, and we will jump to here by go to statement. And that is actually a jump statement, and we finish this, and then with the break we go to 7. So that finish this case switch statement as the assembly code. Control structure number 2, iteration. We have loop, while loop, do while loop, for loop for each loop. Iteration, we have enumerator control, that's index loop. For example, like for loop is called enumeration control loop. So there is a scope for the control variable that's within the for loop and changes to the boundary within the loop. We can change the continue condition, then change it to the loop variable. For example, we using the update condition at the third part of our for loop. Or in the while loop, we can put the update statement at the end of the loop. So you can iterate over element of any well-defined set. Repeat the collection of statements a number of times, and where in each iteration a loop index variable takes the next value of the set of value. So basically this is just talking about we basically has the for I equals 1, I less than 10. So basically we are operating on a set of 1 to 9. That's the set of value here talk about. So for loop, we have initial expression, we have continue condition, we have update statement, and that's the for loop flow diagram or flow chart. And for each loop is a For example, in Python, we have this for each loop. Each time we take one item from the set, and actually this set need to be iterable in order to be able to provide a current value for each iteration. So any iterable data type or something like that can be put into the in set over here. The algorithm is similar to this. So for each loop become popular and become very convenient recently because of its clarity in writing a program. Logically controlled loop, we have pre-test loop, we have post-test loop, for example, repeat until or do while loop. Pre-test loop is the while loop. And then we also have the mid-test loop. We put the test loop, test condition in the middle. But it's actually using the pre-test loop to mimic the function. Iterator. What is an iterator? Iterator actually is a pointer or the reference of a pointer. That means that in there's a data set and we always has a pointer pointing to the data set. And then we use the reference to get the data set using the pointer. So here we have a binary tree. Binary tree actually usually has such a structure. But somehow we have data in here and some node. And the whole thing we need to have certain order. For example, we go this. For example, we go this. We go this, this. Come back. The order, that's the order of iteration. That's the order of the iteration. And then that is the order that the iterator will follow. So that's how iterator can linearize a nonlinear data structure using the enumeration that actually goes through each iterator, each items in the data structure. Let's call iterator. Iterator, Java has the iterable and iterator interface. Usually they are used in combined. Iterator has three functions: next, has next, and remove. Iterable has one function, that's iterator. And the iterator is similar to a constructor. It will return a pointer or a reference variable. And on the right hand side is a binary tree generic type using implement the iterable interface. And then there's a iterator. So there's a class called tree iterator, the implement iterator. And then there's a stack. And then here's the constructor. And it implements the has next function, and remove function because it implements the iterator key type. And this basic function provides you the tree traversal ordering using the iterator. Control structure 2, function and recursion. Control structure number 3, procedural abstraction, recursion, concurrency, and non-determinacy. Here we talk about the procedural abstraction. Subroutine encapsulates a collection of statements, and subroutine calls can be treated as a single statements. Recursion Recursion is subroutines which call themselves directly and indirectly to solve a problem. So basically, first we need to talk about a function f of x. That's a procedural abstraction. And then if f of x somehow call the function itself, now we call it recursion. And concurrency is to branch out two processes at the same time and later maybe joining as a concurrent programming. Non-determinacy is actually provide when there's an alternative construct that actually left unspecified, so it may lead to correct result, but basically on non-deterministic format. It provides some sort of randomness and allow program to actually choose without stuck at a certain condition. So subroutine is function. It has these three major advantage. Abstraction. So you don't really need to know about inside the function. Reusability. You can call the function many times. Library. You can reuse it and then share with other people. Method signature. We have the method. The signature means the whole description, all prototype for the function. Usually you have a name and return type, and you have a parameter list and some modifiers. This we call a signature. And signature is used to identify a function. Same function has the same signature. If it is different, it may be overloaded or overridden. Call stack. When we run a function, it actually will follow for some execution follow, and then jump to some subroutine and continue the call, and then jump to the other one, jump to other one, jump to other one, until it return pop out of the data. So each time when we start, we actually will push some of the return value into the return edges will be pushed into stack, and then one by one we call 4 levels. And there is a call stack that keep track of the return edges and also the parameter and the local variable that we call it call frame. So call frame is a baby data structure in call stack. Exception handling. Exception handling is a special kind of function call, and it is used when we have normal execution flow and something wrong happen. Then instead of halting the program, we actually provide a different route to handle it. Sometimes rollback the function, and sometimes provide the solution to the exceptional case. So we need to know how problem occur, how to create exception, how to store exception, and how to handle exceptions. Excuse me. So right here we have try catch block. And here we have a statement that may cause problem, and that call the function over here, and then call another function over here. And right here, it may have right problem and actually cause IO value, and then we will throw an exception. It look like an outgoing object, and that object pass back to the call level one level above, and it throw again and throw back to here, being catched by the catch block, and then we execute this part. That's the handling of exceptions. But basically, it's similar to a function call. Recursion, equally powerful to iteration, and there is a mechanical transformation back and forth, so each one can be a iteration call using for loop or while loop uh, can be written in recursion as well. But recursion sometimes is more intuitive, and naive implementation may not be efficient. So we need to know about what's the tail recursion that can help you to speed up the iteration. But for recursion, there's no extra program structure need to be had, and it's similar to the functional programming language. So recursion is a subroutine that call themselves directly or indirectly. And usually in mathematical function, we also have the recursive formula, and those recursive formula can be supported by recursion. And it is typical to solve problem that is defined in terms of simpler version. For example, to compute the length of a list, removal of the first element, calculate the length of the remaining list, return n plus 1. Termination condition, we can actually test if the list is empty, then we return 0. So basically, usually it has a termination condition to be handled, and then how to break down the problem using a smaller case to operate a bigger case. And iteration and recursion are equally powerful. They can be changed, be converted from one format to the other. Recursion is more elegant in terms of mathematical sense, but in terms of mechanical operation sense, recursion take more resource and usually is less efficient. So recursion usually is used for functional programming in higher level language, and usually the lower level, the recursion doesn't actually help. So here we have the tail recursion. So what is tail recursion? Tail recursion means like after the recursive call, there is no more operation need to be done. So for example, we have the GCD. We call another GCD function here, but after the call, there is no plus sign or minus sign. Those kind of operation need to be done. Same thing over here. So this one is a tail recursion version of the recursive program. Tail recursive function usually can be optimized by compilers. So that's why we think this is so important. And it actually can be optimized by compiler to provide some iterative code so that when the programmer write in recursion, it can be easily be replaced by iterative program to make it easier to run and also easier to write since it's recursive function. So there is a tail recursion optimization can be done in the compiler. So here is the example for tail recursive format. And as you can see that the core of the this function is tail recursion, and you can actually compile it to similar format like this. And iterative function is also very efficient. So why recursion is not efficient? Number one, it may grow exponentially. Number 2, it has extra epilogue and prologue overhead. So thank you. This chapter 6 is a little bit shorter, but thank you for participating in this session. Bye now.